Okay, let's talk a little bit more about how we like to talk about vectors. So the vector itself is this bold lowercase v. Okay, so this is our vector. When we want to know the magnitude of a vector, we ask for it with these two vertical bars. So this references our vector v. This references the magnitude of our vector v. So it's kind of like you think of absolute value as a single bar. The magnitude of a vector is referenced with double bars. Okay, so some properties about our vector v. If we have a vector v and the magnitude is greater than or equal to 0, magnitude of a vector v equals 0 only in the case that the vector is the 0 vector. Okay, so it's almost too intuitive, right? If I ask for the magnitude of the opposite direction vector as to the vector v, it's going to have the same magnitude. So we'll always get the same magnitude if we're looking at the opposite of vector v, or -1 times vector v and vector v itself. To get the magnitude of a scalar multiple of a vector v, we're going to take the absolute value of the scalar and then multiply it by the vector magnitude here. So absolute value. So nothing's going to be negative. It makes no sense to give a magnitude that's negative. The negative indicates direction. So magnitude is always going to come out either 0 or positive. So that's why they tell us this first. Magnitude is never negative. Okay, we've got a special vector called the unit vector, and a vector u is a unit vector, and it has the magnitude of 1. Okay, so in the case of the unit vector, the only component of the vector that can change would be the direction. So if I start at some point and I go a distance of 1 unit, then I can make another unit vector, has the same length as this vector, but it's just going in a different direction. Okay, so those are all three unit vectors if this distance is 1, but they're different direction. Okay, here we're showing a new way to represent a vector. It's called algebraic, and the reason it's called algebraic is because we're just going to use what we're accustomed to thinking of as ordered pairs, but we're going to put this different symbology around the edges. And all that means is that the vector has been moved so that the start position of the vector coincides, the initial point coincides with the origin in a rectangular coordinate system. Okay, so if we draw our vector and start at the origin of a rectangular coordinate system, we can identify everything we need about the vector just by putting what we would usually refer to as the coordinates and putting them with this little symbol there. So let me change this here. All right, so so for instance, if we wrote the vector, I'm going to make a new vector, we'll call it W, and it's going to be equal to, in this algebraic format, 4, 1. Okay, these little symbols, instead of the parentheses that we're used to, they indicate that this is an algebraic vector, and I can tell that if I go over 4 and up 1, this is the vector I've described. Okay. Okay, this turns out to be really handy. And then how would you make any vector, no matter where it started, how would you make it into an algebraic vector? That's this theorem right here. So if we take the initial point, P1, so it's x1, y1, and it doesn't matter if it's at the origin or not. If we use this technique, we take the terminal point, P2, and we think of it as a vector between starting point P1 and P2, then of course the distance between them is the magnitude. We can move that into the position vector. Position vector starts at the origin, and it's given in algebra. It's capable of being represented in algebraic form. All we have to do is take the terminal point x2 minus x1 and y2 minus y1, and those will give us the two coordinates that represent the very same vector as a position vector in algebraic form. Okay, to demonstrate this, let's say we've got a vector that's described with its initial point at -1, 2, and the terminal point 4, 6. So we've got a picture of that over here. Here's the initial start point. The magnitude ends us at the point 4, 6. So we're going to find the position vector just by giving point 2's x minus point 1's x. So it's going to be a 5. And then the y's, same thing. Point 2's y is 6, and we're going to subtract point 1's y of 2, and that gives us the position vector y value of 4. Okay, so what we've just created is the algebraic form for v, so we can write it now as 5, 4. This little, okay, and then identical vector starts at the origin, has the same distance, and it has the same direction. So it's the same vector. Okay, and this is really useful because it's like a standard. This form of vectors is like, you can think of it like the slope-intercept form of a line, right? If I solve a line for y, then if those lines are given in two completely different formats, general form or something, and I solve them both for y, if they are the same line, it'll identify that in slope-intercept form because we'll have the same slope m and the same y-intercept b. So I say, oh, well, those are differently written in equations. The same goes for vectors. If I reduce any vector to its algebraic form, or what we call the position vector, then if two vectors are equal, we will know right then and there. So v might be somewhere out in space like that, and w might be somewhere else kind of by it, and I might think, oh, those look like they could be identical vectors. If I reduce them into this component form here, then they're going to be identified as the same. And then we will know that, hey, this vector v is equal to this vector w. Okay, again, if we want to know that, let's just write these as, and we'll end up with the same thing for both. And they'll say, yes, v is equal to w. Okay, so this is showing us that if we have I, a single unit in the direction of the x-axis, then we can think of the x component, if I have AB as some vector, we can think of the x component as how many units we're going to go in the x direction. So that's this first component, right? XY ordered pair, A, B, A for x, B for y. So this is just saying if I is called a unit, then how many units are we going to go in that direction? Well, we're going to go A units. So we can really think of this algebraic method of writing it as another method here where we take, let's go A in the horizontal direction, and then we'll go B, and that'll be in the vertical direction. Okay, so what we really need to know is that I can take any vector from this component in direction vector and rewrite it like this. So these are interchangeable ways of writing vector. Okay, once we create those position vectors that are in algebraic form there, say they all start at the origin, and we've got two ways of looking at it. We can look at it like this, or we can look at it like this. So let's say we've got two different vectors, v and w, and if I want to find the sum vector of v and w, I can just take their two components and add those parts together, and these two components. So it feels like and looks just like we're combining like terms in algebra. That's really what this looks like. And then we could rewrite it in either of these forms. And then if we subtract, then I just have to take and subtract each of the components, and that creates my new vector. So what we were doing visually or using geometry before when we added and subtracted vectors, this allows us, once we got the position vector algebraic form, we can start adding and subtracting vectors and getting the result of the new vector. And we can also take the scalar multiple and just multiply each component part to create that new vector. And aha, we've been waiting for this, right? This was a little bit undefined for us. But now that we've got this form here, okay, the direction, the magnitude in the direction of the x and the magnitude in the direction of the y, we can take and find the magnitude of the vector, which we said was double bars on each side. Mathematically, that's going to be the square root of a squared plus b squared, okay, if our vector is so defined. That's nice. Okay, so now let's use algebra to find the sum of two vectors or the difference of two vectors. So these are understood to be in the algebraic form. So the initial point is at the origin, and it goes a magnitude of 2 in the x direction and a magnitude of 3 in the y direction. And so we can rewrite it as 3i minus 4j, because I is 1 unit in the x direction and j is 1 unit in the y direction. Okay, so w and v are so described. So if I want to take v and add w, I just have to add their component parts. So that's going to be 2 plus 3, and then 3 plus negative 4, or 3 minus 4. Okay, so we're going to get 5, negative 1. And let's say we wanted to write that in this format, then that would just be equal to 5i minus 1j. Okay, so that's part A. Let's take a look at B. We're going to take v minus w. Okay, so I'm going to take v, subtract that 3, so that's the 2 minus the 3. Now I'm going to take the 3 minus the negative 4. Okay, so we'd end up with a vector negative 1, 7. Alternatively, we could write that as negative I plus 7j.